Today we're talking about writing redox half reactions. When we write half reactions for these oxidation reduction reactions, the first thing we have to do is to write them as net ionic equations. We've done this before. The next thing we have to do is to determine the substance that's oxidized and the substance that's reduced. We've also done that before. And with those two pieces of information, we can then write the oxidation half reaction and the reduction half reaction for the reaction. And we're going to see how that plays out in this first example. In this first example, again, we want to write it as a net ionic equation. Since both copper and silver are elements, they're not going to be obviously able to ionize, but both silver nitrate and copper nitrate are ionic. And when they're ionic, remember, we need to know whether they're soluble or not. Both of them are soluble, so both of them are going to ionize. They're going to ionize here. And one thing I do as a shortcut is once I decide how they're going to ionize and what's going to split, if you will, then I want to look for my spectator ions before I write them down in the ionic equation. It just saves me a little bit of time. So if you'll look for something that occurs on both sides of the arrow as part of something that ionizes. So you're only looking for the things you slashed through. And if there's something in both of these substances, even though they aren't the same number, then they're going to drop out as spectator ions. And if you notice, both of these nitrates are going to drop out as spectator ions. Now what I always do next, because remember, if it splits, it gets a charge. If it splits, it gets a charge. So put your charges up there so you won't forget to write those down whenever you get ready to write this as net ionic. So now that we have it this far, we can go ahead and do this net ionic equation as Cu plus Ag plus, yielding Ag plus Cu, 2 plus in this case. And now we can find what's being oxidized and what's being reduced. Since both copper and silver, metallic copper and silver have 0 for an oxidation number, this is going to end up leaving copper as a substance that's oxidizing and silver as a substance that's reducing. Now, the reason I like to draw these arrows is not just to emphasize that oxidation reactions increase in oxidation number and reduction reactions decrease in oxidation number, but these arrows also help us decide what goes to what in our half reactions. So I'm going to be looking at an oxidation half reaction of copper forming copper 2 plus, and my reduction half reaction as the silver ion Ag plus forming metallic silver Ag with 0 for an oxidation number. The last step of this is to figure out what's happening to our electrons. This is the point where we're going to decide how those electrons are transitioning. And if you look at copper and copper 2 plus, the way we want to add our electrons is to put them, remember electrons are negative, we're going to put them on the side that will cause the charge on both sides of that arrow to be equal. Either both sides 0, both sides plus 3, both sides minus 2, whatever will make both sides of that arrow equal. And if you think about it, if you add your 2 electrons to this side, that's going to give us 2 positives and 2 negatives, which is going to give us 0 overall, which is going to match the 0 on the other side. And oxidation number, since oxidation is loss of electrons, those electrons are always going to be on the right-hand side for an oxidation reaction. Now for the reduction, in order to get those charges to balance, we're going to need 1 electron on this side. That 1 electron will balance the +1 charge from silver, so we'll end up with 0 for our overall charge on the left-hand side of the arrow, which is going to match our 0 for the silver metal atom. So that's our half reaction. Those are our half reactions for that particular redox reaction. Well, let's go on to the next one. I'm not going to spend a lot of time describing what happens with writing the net ionic equations because you've done that. And you can go back and listen to those notes if you're having a little bit of glitch on that. But over on this right-hand side, all of these are molecular, this one being a molecular or diatomic element. So none of those are going to ionize. On the left-hand side, both of these are strong acids. And remember, strong acids, 2 of the acids on our 8 strong acid list from previously in the notes, those are going to ionize. The hydrogens are going to split off. There's nothing on the 2 sides of the equation that are going to cancel out, that are going to act as spectator ions. So let's just write down now what we've got for our net ionic equation. We've got the hydrogen ions coming off, nitrate coming off as an ion. Now I could write down the hydrogen ion from HI again, but since I've already got it over here, I'm not going to write it again. I'm just going to write down the iodine portion. There's no need to write it twice. It's just redundant. So over here, nothing is going to ionize, so I'm going to leave those as they are, just carry them down. Now that I've got my net ionic equation, I want to find my charges, find my oxidation number, so I can decide what's changing in charge. We've already established that this hydrogen is positive, that this iodine is negative. Over here, that iodine is going to be 0 because it's in its elemental form. H2O is always going to be +1 -2, +1 for hydrogen, -2 for oxygen. NO is easy. Since oxygen's a -2, that means this nitrogen has to be a +2. So finally over here with nitrate, we know the oxygen's -2. The only time it's not is when it's an element or when it is part of a peroxide. Since that's a -2, but there are 3 oxygens, that's going to give us a total -6 charge. Now, please be careful here because I see too many times people saying, okay, the nitrogen must be +6. No, it's not, because nitrate is a polyatomic ion. So when we set this equal to something, it must be equal to its charge, -1. So if that's true, nitrogen must be a +5 in this case for those charges to equal out, or those oxidation numbers to equal out to -1. So nitrogen here is a +5. So now we can quickly see what's being oxidized and what's being reduced. Notice that iodine is going from a -1 up to a 0. There's our substance oxidized. We've got the nitrogen going from, and I'm going to go ahead and erase these numbers down here so that we can see it maybe a little bit better. It's going from a +5 to a +2 state, so that's what's being reduced. So now I can write our half reactions. We've got I- going to I2, and we've got NO3- going to NO. Now here's an example of a couple of things that you're going to run into. First of all, we must balance by mass and then balance by charge. So balance by mass first, and then go back and balance by charge. So with our iodine, the first thing we've got to do is to come back in here and say, okay, there's 2 iodines on the right, so we must have 2 iodines on the left. So that's going to balance out our iodines by mass. Now we can think about charge. At first glance, it looks like we're going from a negative charge for iodine to 0. That looks like it's just a 1 electron change. But this is a very, very often missed situation. It's when we've got 2 atoms in play, 2 ions in play. There are 2 iodide ions being transformed into an I2 diatomic atom. That is a -1 to 0, a 1 electron change, but it happens 2 times. So this is actually going to be 2 electrons involved, because look at what your charge is going to be. I'm doing this in green because I don't want you to put this on your final answer, but look at your charge. You've got 2 negative here and 2 negative here. You've got to make sure that those charges balance. Now the next one, we're going to learn more about balancing out oxygens and balancing the overall redox reaction in the next set of notes. But for today, all I'm worried about is that we make sure that we balance by mass and charge for the actual element that's changing charge, that's changing oxidation number. Now I'm going to put this in because generally we don't show this. I'm going to do this in green. Remember up above we said that this nitrogen was a +5 and that this nitrogen was a +2. So we need to get those balanced by mass, and they already are. There's one nitrogen on either side, and then by charge. We're going from a +5 to a +2 for the nitrogen. We don't care about overall charge right now. We just want to know that we're going from a +5 to a +2. That's a 3-electron change. It only happens once, so that's what we're going to put, is that 3-electron change, because that +5 and the 3 negative is going to give us a +2 on the left-hand side, which is going to match this +2 over here. So that's what I want to see. Now remember, in our final, let's see if I can get these erased without erasing everything. We don't want to see that green in that final answer. So let me see if I can repair this a little bit. This is what we want it to look like. So what about the next one? Got a couple more examples here. I just wanted to make sure that there weren't any surprises on your assignment. In this case, the only things that are going to ionize are the ammonium chloride and zinc chloride. Everything else is either molecular, an element, or it's an oxide, which oxides don't ionize either. So if you notice, both of these two ionized substances on either side both have the chloride ion in them. So we can X those out. Make sure you remember that you've got to get that charge back in there, so you won't forget to do that whenever you rewrite the equation. So we end up with zinc plus manganese dioxide plus the ammonium ion, yielding the zinc 2+ ion plus MnO2O3 plus ammonia plus the water. And now we assign charges. We know zinc is going to be 0. We've already established over here that this zinc is a 2+. The manganese and oxide here, oxygen's -2, that gives us a total -4 for oxygen, which means manganese must be a +4. Ammonia and ammonium are always the same. And some things you just want to know charges on because they happen so often. Nitrogen's a -3 here, oxygen a -1, or excuse me, +1. Over on the other side, nitrogen -3, hydrogen a +1. Water, of course, is always +1 for oxygen, -2, excuse me, +1 for hydrogen, -2 for oxygen. So the last one that we need to do is M2O3. Remember, if we have a 3-2 or a 2-3 combination, we can do what we call cross charges. This means since oxygen's -2, manganese is going to be a +3. So there are charges, and let's look and see what's changing. Looks like zinc is going from 0 to +2, so there's our oxidized. Manganese is going from +4 down to +3, so there's our reduced. So oxidation is going to be zinc forming Zn2+. And we've already established in this oxidation-reduction reaction, we've seen one very similar up above, that we're going to end up with our 2 electrons on that side to balance out the zinc's 2+ charge. So now let's look at the reduction half reaction. We've got MnO2 forming Mn2O3. Now remember our rules up there in green, balance by mass and then by charge. And we're worried about not the oxygen, but the manganese, because that's what's changing charge. So we need to get that balanced first of all. So the first thing that we need to do then is to put a 2 in front of MnO2, manganese dioxide, so that we have our 2 manganese atoms on both sides. Now that we know this, I'm going to put it in green. Remember, we don't want to see this in the final answer. But up above, we established that manganese was a +4 on this side and a +3 on this side. So that looks at first glance like a 1 electron change, but remember, we have to take into account how many times it happens. We're going from 2 4 pluses, which is a +8, to 2 3 pluses, which is a +6. We've got that 1 electron change twice. 2 electrons on this side. Those 2 electrons are going to balance out that charge, so we end up with a +6 for the manganese on both sides. So that's our half reaction for the reduction half reaction for this particular redox equation. Okay, our last one. Let's look at what's going to ionize here. We've got potassium is going to ionize with that ionic compound. We know potassium always is soluble. So those two are going to ionize, and there's potassium in both of them, so let's get rid of those. If you look up dichromate, it's a 2 negative. You should be able to see that anyway since it's with 2 potassiums. And hydroxide's a -1. Nothing else is going to ionize. They're all either molecular or oxides or elementals. So we're just going to rewrite this, Cr2O7 with a 2- charge, plus water, plus sulfur. That's going to leave us with a hydroxide plus Cr2O3 plus SO3. So there's our net ionic equation. Now let's find our oxidation numbers. We've got oxygen at a -2. That's a total of a -14. Remember, this has to equal out, since it's a polyatomic ion, to its charge. So that's going to have to equal out to -2, which means the total chromium charge has to be a +12. But there are 2 chromiums equaling +12, so 1 chromium is going to be a +6. So that's how we figure out the oxidation numbers for dichromate. Water, as usual, is going to be +1 for hydrogen, -2 for oxygen, 0 for elemental sulfur, -2 for oxygen, +1 for hydrogen in the hydroxide. A 2-3 combination, so cross charges. And finally, for the last one, -2 for oxygen, but there's a total -6. This is not sulfite. This is sulfur trioxide. If it were sulfite, it would have to have been with another element, a metal up here in the original equation, or it would, if it were sulfite, it would have had to have shown that 2- charge. So this is the compound sulfur trioxide. So it's got to equal 0 just like any other compound, which means that sulfur has to be a +6 here. So those are our oxidation numbers. So let's see what's changing as far as oxidation number is concerned. We're going from a 0 to a +6 for sulfur. So there's our oxidation. We're going from a +6 to a +3 for our chromium. So there's our reduction. So let's look now at what we're going to write for our oxidation reduction half reactions. Oxidation is going to be sulfur going to SO3. Now I'm sure y'all are going nuts over this whole oxygen thing and those not being balanced. But again, we're going to learn that next time. I want to take this a step at a time. All we're worried about is sulfur. It's already balanced by mass, so now we simply have to tell what's happening as far as our electrons are concerned. Remember up above, we decided that this was 0 and that this sulfur is a +6. So what we have here is a 6 electron change. So we're going to need to add 6 electrons to the right-hand side. And now for our reduction, we've got Cr2O7 with a 2- charge going to our Cr2O3. Remember what we put for those charges. We said that chromium was a +6, and over here that this chromium was a +3. So at first glance, it looks like this is a 3-electron charge, a 3-electron change. Why is it not a 3-electron change? Because it happens twice. We're actually going from 2 chromiums, which is a total of +12, to 2 chromiums on the right-hand side, which is a total of +3, excuse me, +6. So that total +12 to the total +6 is actually a 6-electron change. So we need 6 electrons here to balance that out. And when we do, we end up with an equivalent charge on both sides, from a +12 on this side total, as we talked about. With those 6 electrons added in, it's going to equal +6, just like the right-hand side does. So if you get rid of that green from those equations, that's what I want to see on your final paper, your final work for your assignment.